Let's wait for a few minutes, then we will start. ये खुद ना दिखे सब रिकॉर्ड हो गए खुद ना दिखे सब रिकॉर्ड होते हैं বলছি রেকর্ড হচ্ছে তো বেশি কথা বলছে আরো যত বলছে hello I am audible right can anyone confirm hello am I audible hello please confirm someone is my voice clear Okay. So please, guys, interact with us. Otherwise, it will be difficult for both of us to conduct the sessions. Anyway, we'll start with this problem. Similar problem I have done in the previous session, but again, once again, a bit of different. So a flat surface is covered with non-overlapping discs. These are the discs of same size. And the question is, what is the largest fraction of area that can be covered with these sort of this? So options are given. Please try to solve it, and then after a few minutes, I'll solve it. You can look at the previous session's solution. I mean, it's very similar to that. Just it will. Anyone found the answer? Okay. So let me solve it. So we need to find the largest fraction area that can be covered, right? So you have these circular discs. Let's say radius of each circular disc is r. Then area of disc will be pi r square. Each disc basically. Now observe that with two circular discs, this and this, let's say this is the diameter of a particular disk, right? So 2r, and this diameter forms a equilateral triangle like this one, right? So the diameter of a disc is equal to the uh, side of equilateral triangle, right? Let's say this is A. 2 are equal to A. Now, then the area of each equilateral triangle equal to root 3 by 4 into side square, A square. Root 3 by 4 into 2r square. Root 3 r square unit. Okay. Now we need to find how much fraction does it cover with this circular disc. For that, we need to find, so how many circles are there, right? So let's say in a particular triangle, how many circles or how much portion of a circle or disc is there, that we need to find. So that can be easily find if let's say you observe that this portion, let's say this portion and this portion, like this one, there will be uh, six equal portion, right? Like this one, 1 2 3 4 5 6. So 6 equal portion, a disc is divided by this triangle by 6 equal portion. Now how much a triangle gets in its area? So 1 2 and 3, right? So then the fraction, largest fraction of area is largest fraction of area covered will be 3 by 6 into area of each disk. So you understand that 3 by 6, why 3? Because one triangle takes into three part of its, right? Three portion. Now how much portion of a disk is that? 1/6 portion of a disk it covers. In this area is 1/6 of that disk. Now like this one there is 3, another 2 basically, so total 3, and then divided by the total area of this equilateral triangle, right? Root 3 r square. So if we calculate this, this will be pi by 2 root 3. So the correct option will be D. So largest fraction of area covered is pi by 2 root 3, and this is also called the packing fraction. I don't know it has been covered in the lectures or not, but this is also called packing fraction. It refers that given a crystal, let's say we talk about the familiar cubic crystal. There are atoms at the corner, simple cubic case. Now, in an unit cell, cubic unit cell, right? How much of this volume is covered by the atoms? There are some spacious place, right? If you look at the simple cubic case, then on the only cornered atoms are there, right? There is no body centered atom or face centered atom. So there is space in the unit cell. So how much of this unit cell is filled. This is represented by the packing fraction. How much filled with atoms or anything else, molecules, etc. So this is called the packing fraction. So in this case, this is the packing fraction. Okay. Okay. So I hope you understood it. If you have any question or doubt, please ask. Also, can anyone confirm that how much of it is covered up to week 3? I mean, X-ray diffraction, the formula 2D sin theta equal to n lambda, like this one. Is this covered or not? Can anyone confirm, please? Okay. Oh my God, the right answer. Yeah, Kalpana. Hello. Yeah, week 3 that I have seen, but how much of it is, I mean, the concept that covered, does it include this formula 2D sin theta equal to n lambda and all those things? Okay, 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 fine. So we'll do this problems based on this formula in the next session. I'll
Sir,
focus.
I think SAR will be covered crystal structure,
Mm-hmm.
diamond, sodium, and NaCl. Last two videos I have not watched, sir. Tomorrow I tell you, or otherwise next class, sir.
Okay,
I
okay.
think HCP,
Mm-hmm.
sodium chloride, and remaining crystal system, everything finished, sir.
Okay, okay. So we are still.
Reciprocal.
Mhm. Okay, so we are still primarily on the crystal structure, right?
Yeah, 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 sir.
Okay, okay, okay. Thank you. So let me give you the problem based on crystal structure itself. Na is the Avogadro number. Also, it is given that molecular weight of NaCl is 58.5 kg per kg mole. So you have to find the lattice constant of NaCl crystal. The information is density, Avogadro number, and the molecular weight. So please try to find out, then I'll solve. Okay, so one information is not given here. That NaCl crystallizes in which type of crystal? Cubic crystal, BCC, FCC, or simple cubic. So it crystallizes in the FCC, okay, face centered cubic, not BCC. Okay. So let me solve it. So just a simple application of formula will do the job. So we know the density within a crystal, or let's say unit cell, is given by N M by A cube Na, right? So where N is the number of atoms in the unit cell. In this case, in our case, this is FCC, so 4. M is the molecular weight, and A is the dimension basically of that unit cell. This is A. So A cube is the volume, and this other terms includes the mass present in the unit cell. Unit cell. Okay. So we need to find the dimension. So this will translate into Nm Na rho on third. So N is 4, M is 58.5, N is 6.02 into 10 to the power 23 into density is given as 2.189 kg per meter cube. So if we find this one, This will be around 5.61 into 10 to the power minus 10 meter, which is 5.61 angstrom. Screen not visible.
No, sir. Visible, sir.
Okay, okay. Okay. So the dimension is 5.61 angstrom. Okay, this is the answer. So reciprocal lattice introduction has been done, right? I mean, how to convert that reciprocal lattice vector to the normal primitive unit vector. Can anyone confirm? Okay, okay. So I'll give a problem based on that. Capital A, B, and C represents the reciprocal lattice vector. Okay, so the primitive translation vectors of a BCC lattice are given by a equal to a by 2 x cap plus z cap minus, sorry, x cap plus y cap minus z cap, b equal to a by 2 minus x cap plus y cap plus z cap, and c equal to a by 2 x cap minus y cap plus z cap. Now we need to find the primitive translation vectors for the reciprocal lattice. Okay, options are given. Please try. So anyone found the answers? Just some algebra. Okay, I'll do, but let's see. Okay, let me solve the problem. So, what is the formula for reciprocal lattice vector? So, the formula is 2 pi into, so let's say this is the first reciprocal vector A, P cross C by A dot B cross C, right? Similarly, B will be C cross A A dot B cross C, and C is okay. So let's find out A dot B cross C first. That is common in everywhere. So B cross C will be A by 2 minus X cap plus Y cap plus Z cap cross. Okay. Now X cross X, this will be 0, right? X minus X cross minus Y will be X cross Y equal to Z cap. Similarly, minus X cross Z will be X cross Z is usually minus Y, so it is Y cap. Similarly, Y cross X will be minus Z cap. Y cross Y will be 0, and then Y cross Z, this will be plus X cap, and Z cross X is plus Y cap. Z cross minus Y is minus X cap. So overall it is plus X cap, and Z cross Z is 0. So it is 2 X cap plus Y cap. So A dot B cross C will be A by 2 dot. So X dot X is 1, X dot Y is 0. Similarly, Y dot X is 0, Y dot Y is 1, right? And Z 0. Z part, Z dot X or Z dot Y, both are 0. A cube by 4, X dot X is 1, Y dot Y is 1. So finally A cube by 2. This is A dot B cross C. Now to find A, capital A, we need to find B cross C. So the formula is 2 pi B cross C A dot B cross C. So B cross C we already find out that this is A square by 2 X cap plus Y cap, right? So 2 pi into A square by 2 by A dot B cross C is A cube by 2. 2 pi by A into X cap plus Y cap. Okay. So this is A. Similarly, we can find out that B will also be 2 pi by A Z cap plus Y cap, and C will be 2 pi by A X cap plus Y cap. Okay, so these are the answers. So the correct answer is D. and notice that this was given as BCC lattice. So the primitive translation vectors of BCC lattice are these, and we find out the reciprocal lattice vector for this BCC lattice are these. And if you notice, these are the actually primitive translation vectors for FCC lattice. Okay, so the reciprocal lattice vector for BCC is FCC lattice primitive vector, and FCC lattice reciprocal vector will be the BCC lattice uh, primitive vector, vice versa basically. Okay, so let's find out the Miller indices. Okay, so you mean the third question, right? This one, reciprocal lattice vector. Parasuraman. Okay, so which part? Tell me to stop. Just unmute and speak.
Sir, I want the calculation part. Yes, sir. Yes,
Okay,
please.
okay.
Please.
Yeah. Anyway, these will be made available, I think, through the NPTEL portal. But anyway, not an issue. Let me know when it complete.
Sir, this recorded video is available in details.
Lecture notes, we made it available to them. Now what they do it, I don't know. Matlab, I have not seen in the NPTEL portal.
Uh, okay. I'm happy, sir. You can proceed further.
Okay, okay. So the options are so find the Miller indices where the plane intersects at these points of a crystalline axis. So it will be like A axis, B axis, C axis, and the plane is somewhere 2A, 3B by 2, and doesn't intersect anywhere in the third axis. So plane is somewhat like this one. Basically parallel to C axis. Just try to find out and then I will solve. ফ্যানটা একটু জোরে দাও তো। Option C. No, Renuka. No, it's not B even. Any more answer or options? Anyone solved it? Okay. Yeah, I made a small mistake. So this should not be infinity. This should be 0 option. So then
That means I think D option, sir.
hello? What?
Correct option D?
Yeah. Correct option will be D, but there should be a 0.
Yeah, infinite. If you replace the infinite, you put the 0 means okay.
Right. Okay, let me solve it. So the way we find Miller indices is that crystallographic axis dimension A by that intercepts basically. So here 2A is to B, this crystallographic axis dimension, 3B by 2 is to C by infinity. So it will be 2 by 3 is to 0. If you do LCM of all these, so it will be 3 is to 4 is to 4. Sorry, 0. So this is the correct answer. Sorry, I gave wrong option. Okay, so one problem not exactly related to the crystal structure, but preliminary is that in week 0 or some part of week 1 may be covered. Okay, so the question is, for a randomly picked conduction electron in metal at time t equal to 0, the probability density function for electron to have collision with an ion at time t is given by this function 1 by tau e to the power minus t by tau. Tau is basically a constant, which is kind of time scale for electrons. Now the average of the square, mind it, this says that average of the square of the time interval for the electron to have its next collision is given by this option: tau square, 2 tau square, tau square by 2, or tau square by 4. So picture is something like this. So there are billions of ions in the metals, let's say, and there is one electron or many other, but let's focus on one electron, and it starts its journey from here t equal to 0, and the probability that it will collide at time t with some ion, let's say this one, is this p of t function. Okay, now we need to find average of the square of the time interval for the electron to have its next collision. So this was the suppose first collision, then this will be the second collision. Now there will be some time interval between this and this collision. We need to find that average of the square. So we need to find initially the time between these two consecutive collision, and square of it, then average it, right? Average of the square of the time interval. So this is what we need to find, time square and average of it. Okay, so I think this gives the hint how to find it, right? This is average and this is time square. So try to find out. Okay, so I'll give you the further hit. So you just need to find out uh, p square average, and you think about the probability problem. So how do you find out average of some function where the function is p square, given that probability density is p of t, right? We have given a function's probability is p of t. You just need to find out the average of it. Anyone find out?
Sir, you can explain, sir.
uh, okay, so you want me to solve it? I will anyway solve or explain the problem so that you can try. Hello. Okay, so let me solve it. Actually, So once again, let me briefly explain that what is at our hand. So there is billions of ions in a systems or like metals. Now randomly picked conduction electron. Let's focus on this electron. Now this will have basically collision with ions, right? And it is not that the electrons will collide with each and every atom, so or the ions. It has a probability density like this one, and at some interval of time, let's say given t1, it has some probability of colliding with these atoms or ions basically. Okay, so now let's say at t equal to 0 there is first collision happened here. Okay, now next collision at some t equal to t, let's say time equal to t, that collision will happen with this atom. That probability is given by this pt function, probability for yeah, happening collision. What we need to find out that there is some time interval t, right, between these two consecutive collision. We need to find out the average of the square of this time interval. So average we need to find, average of what? Average of square of that time interval. So this is what we need to find, and this is true for any probability function. If you have given any function and we need to find that average, right, any function, so integrate with that function, with that probability distribution of that function, and let's say x is the variable, right? So this is what the general formula is. So in our case this will be like we need to find t square average, right? So t square average will be t square, the function itself, probability of distribution of the time, and dt. So what will be the limits here? Limit will be at t equal to 0, the collision happens. That is one thing, and the time may extend to infinity. Up to infinity time, there is no collision. It may happen. Probabilistically, it is very much possible, right? This is what this probability distribution also says. If you send t tending to infinity, then there is no collision. Pt becomes 0, e to the power minus infinity, right? And at t equal to 0, it will have some finite probability of collision. Okay, so the limits will be 0 to infinity t square pt dt. So 0 to infinity t square 1 by tau dt. Okay, now for simplicity we can assume that t by tau equal to x, so that dt equal to tau dx, which converts this equation into so 1 by tau t equal to x square tau square, 0 to infinity limit remains same, and then e to the power minus x dx, right? And with dx there will be another tau, so it will be tau cube and tau 1 by tau square, 0 to infinity x square e to the power minus x. Okay, so I'm not solving that integral. This is very easy integral. You just, and the limits are also very feasible, 0 to infinity. So you solve this integral, you just find out that this is 2 tau square. This solution of this will be 2. Okay, so this is our answer. Average of square of time interval between two collision is 2 tau square. So this is the right option. Okay, so everyone understood it? You may want to copy it. Please let me know if you have any doubts. So, are the question becoming harder, or it's just okay to have this kind of questions? Can anyone tell? Otherwise, things will be very repetitive. I mean, having almost 7-8 tutorial session, including other TAs on the crystal structure itself is not that much feasible. I think the question or the question type will overlap with each other. Okay. Okay, so next question is, a metal suffers a structural transition from FCC to simple cubic structure, and it is observed that this phase transition of this structure doesn't change any volume. Okay, so need to find out the nearest neighbor distance, DFCC, nearest neighbor distance for FCC, and then DSC, simple cubic. So these are the options. So try this out. Similar type of problem we have solved in the previous session itself, right? So anyone have any idea how do you solve this problem?
Sir, nearest neighboring distance means I think coordination number.
Uh,
Otherwise, radius 2 or distance.
right. It's like coordination number.
Yeah.
So in coordination number, we find how many atoms are there, right? Here we need the
Yes, sir.
distance.
Yes.
Here we need the
Here,
distance.
once again, you can explain, sir. No idea.
Okay, so I'll explain the problem, but if we can't solve it, then we'll solve. So initially we had some FCC structure. FCC means like this one. There will be two corner atoms, and then there is at the surface of this surface. There is of course corner atoms at the behind. All these corners are filled, and there is in each surface there is an atom. Okay. So this was the previous structure. Now it gets converted into from FCC to simple cubic. Simple cubic means this type of atoms only at the corners, right? So this has been converted. Now we need to find the nearest neighbor distances for these ratio between these two systems, so FCC and simple cubic, given that the volume remains same. Okay, so the nearest neighbor distance for FCC will be what? So you need to find out this nearest neighbor distance between two atoms, right? So these are the three atoms that touches each other. So we first need to find out the nearest neighbor distance between in the FCC phase, okay, between the atoms. So we need to find out DFCC first. What is DFCC? And then we need to find out this nearest neighbor distance between two atoms in the simple cubic phase. So D simple cubic, what is that? Uh, then you need to find out DFCC by DSC. What you will get is some kind of answer in terms of lattice vector, right? Or let's say lattice dimension. AFCC is the lattice dimension, this one for FCC, and this one, let's say ASC, right? In terms of AFCC and ASC, you will get. Then you need to use this information ki it doesn't change the volume when it got converted from FCC to simple cubic, which will give you the relation between this one, right? If it doesn't change the volume, then there will be definitely some relation between this one, right? So you need to use that to find this one. This is the final aim. Someone says option C, Pavitra. Option C. No, not option C. Try this out. I'll solve. And by the way, nearest neighbor distance means center to center distance. Okay. So this center to center, this distance is nearest neighbor. Okay, so let me solve it. let's first find out the nearest neighbor distance of FCC and simple cubic. So for FCC, it will be like this one. I'm drawing like a rhombus, but it's actually square, right? Because we are in the cubic crystal. So the atoms will be some sort of, these are equal, but sorry. And this is, let's say, AFCC, dimension of FCC crystal. Okay, so I'm showing this one face. Let's say this face, this face. Okay, so okay, so this is A, and what we need to find out that nearest neighbor distance. So this distance or this distance, same as that. Now this is also A, this distance is also A FCC, right? So the overall distance, this one will be, let's say this distance, let's call it R FCC, right? R is just the diagonal of a square, right? So diagonal of a square will be 2 and a side root 2 AFCC. Now this is the total. We need to find out this distance. So then DFCC will be RFCC. Someone said answer is 0.707. I think no, it's out of option. Let's find out. So the DFCC, this distance, DFCC is RFCC by 2. So AFCC by root 2. This is DFCC. Okay. Now for the simple cubic case, it is just like this. So there will be cubic atom like this one, cubic atom like, sorry, circular atom like this one. Okay. This is a simple cubic. This is also a simple cubic. And this is again diagonal. So, okay. Yeah. Not really, we need to find out diagonal because to find out the nearest neighbor for simple cubic, that both these corner atoms itself are more nearest than this diagonally different atoms. Okay, so this is the nearest neighbor distance for simple cubic, and this is also the dimension of the simple cubic. So nearest neighbor distance for simple cubic is just the dimension of the simple cubic unit cell. Okay, so we'll find out both of these now. In so what we need is DFCC by D simple cubic. So AFCC by root 2 into a simple cubic. So then we need to find out relation between AFCC and a simple cubic, right? So for this, we'll use this information that when it gets converted into FCC to simple cubic, there is no change in volume. Okay. So volume doesn't change. And it is the same material, metal, let's say, metal that converts into SC from FCC. So the mass is invariantly same, right? Same metal, same amount of metal gets converted. So mass remains same, volume also remains same. So then density in the FCC phase will be density in the simple cubic phase. Now, what is the density? Let's say, so the density will be 4. There are 4 number of atoms per unit cell in FCC phase by a FCC cube, and there is only 1 atom per unit cell for the simple cubic case, right? So this will be the density. It's atom density, let's say. So then a FCC by a simple cubic will be, sorry, this will be cube, 4 to the power 1 by 3, right? This is the relation we got. Now we got this one, dFCC by d simple cubic. So finally dFCC by d simple cubic equal to AFCC by root 2 a simple cubic. AFCC by a simple cubic is 4 to the power 1 by 3 by root 2. So it will be that. So 2 to the power 2 by 3 in this one is 2 to the power 2 by 3 minus half. So 2 to the power 6 1 by 6. Yeah. So 2 to the power 1 by 6, which is around 1.122, should be around this. Or if anyone have calculator, can you find this one? 2 to the power 1 by 6. Just to check with Pavitra, is he or she right? No, 2 to the power 1 by 6 is around 1.122.
1.12.
Right,
Correct, sir.
right. So this is the answer B. So please tell me if you don't understand the concept of this problem, or how do we approach. Okay, so let's move to the next problem. So the next question is lattice parameters ABC of an orthorhombic crystal are related by A equal to 2B equal to 3C, and we need to find out in units of A, this one, first crystallographic axis, the interplanar separation between the 110 plane. Okay, and I don't know it has been covered or not, but let me tell you. So if we have the Miller indices, let's say HKL of a plane, and then the crystallographic axis dimensions are ABC, then the interplanar distance between two consecutive planes, two consecutive parallel HKL planes, given by this formula: h square by a square plus k square by b square plus l square by c square. Okay, so this is the interplanar distance between two HKL planes. So you will use this formula to solve this problem. So here given HKL is 110, right? Anyone trying to solve the problem?
Sir, I think 1.118.
No, okay, in units of A, right? You need to find out the distance in units of A, this one, right? This one. Even then, 1.118 is not the answer. Okay, so let me solve. So given HKL, in our case is 110 plane, right? We need to find the interplanar separation between 110 planes. So if we apply this one, D110 equal to 1 square by a square plus 1 square by b square plus 0 square by c square. Now in this way we'll get the answer in terms of a and b, right? But we need to find the interplanar distance in units of a, and for that we have the information given: a equal to 2b equal to 3c. Yeah, so then we can assume that a is itself a, and then b is a by 2, not assume, from this information itself. C equal to a by 3. So if we apply this, 1 by a square plus 1 by a square into 4, right? So what will be that? Root 5, a by root 5. So this will be around 0.447 a, right? This is the right answer. Okay. No, not half. Okay, so next problem. So the last problem will be solved. Okay, so atoms are assumed to be hard sphere of radius r, capital R, and which is arranged in an FCC lattice with lattice constant A. Okay, now such that the atom touches its nearest neighbors, which is obviously true for this FCC lattice. Now take the center of one atom as the origin. Another atom of radius r, small r, is to be accommodated at position 0 a by 2 0 without distorting lattice. What do you mean by without distorting lattice? There will be no displacement of the previous atoms, this r. Okay, previous atom of radius r. Then we need to find out the maximum value of r by small r by capital R. Just think about a bit. Any idea? So anyone have any idea? How do we solve this? Just draw an FCC lattice and try to understand how the question is saying. You'll get some idea. Okay, let me solve it. So given that FCC lattice, right? So the greens are the corner atoms, and yellow is the uh, face-centered atoms. Basically, I have not drawn all the face-centered atoms, but some. So this lies in this plane, right? And this lies in this bottom plane. Now these are the usually face centered atoms in the face centered lattice. We need to accommodate another atom of a different radius, small r, where So let's say this is the origin, this is my origin, and I need to accommodate the atom of small radius at this position. Let's say this is a by 2, this is y axis, right? So 0 a by 2 0, so 0 0 a by 2 and here 0. So in y axis there are these atoms which have radius r, capital R. This atom also has capital R, but this atom has radius small r. Okay, and we need to find that small r by capital R max, given the condition that there should not be no distortion in the lattice, so that this atom doesn't get displaced from its own positions. Okay, so what we can find from this color, so this part, I am not touching the atoms each other because this will be very congested then, but these will touch with each other. Okay, this capital R, this small r, this capital R. So if A be the dimension of the unit cell, let's say A is the dimension of the unit cell, then what will be that from this y axis? So if I draw it like this one, so it will be like this one, small r and then capital R. So this is capital R, this is small r, this is again capital R. So this will be this small capital R, this capital R, and then it is 2r. So 2 smaller plus 2 capital R, right? Now for a face centered system, we already in this okay, so this is one condition, let's say one. And for a face centered system, if I draw a face of this face centered system, then this is a unit cell parameter, this is capital R, this is the face centered atom which itself has, this is 2r and this is r. So another relation emerges, this is also a, so root 2a, which is the diagonal, this one equal to 4r, right? This is equation 2, let's say. So from this we find that r equal to root 2 by 4a. Now we put this information to this equation 1, then a equal to 2r plus root 2 by 4 to a, right? So just need to find out the r smaller, so it will be like smaller will be half a 1 minus root 2 by 2 a, right? This is smaller, equation 3, let's say. And capital R we already know, equation 2 itself. So the ratio of r by r, capital R, is half 1 minus root 2 by 2 a by this one. So if we just do some algebra, simple algebra, it will be around root 2 minus 1. So 1.414 minus 1 equal to 0.414. So this is the correct answer. Okay. Without distorting the lattice, the ratio between small r and capital will be 0.414. So usage answer is 2. No, anyway, so understood the concept. This
Yes,
was
sir.
a
Yes, sir.
okay. So this was the last problem of this session. I hope NPTEL will release more lectures beyond crystal structure, let's say. Otherwise, it will overlap the questions. But before ending, so can you please tell me from which background you are? I mean, different people, so UG, PG, engineering, etc. Everyone, please tell me. That will help us to structure the problem, or let's say assemble the problems accordingly. It will follow the NPTEL guidelines, but anyway. So most of the people are from UG or PG.
I think this is this course in the UG level, sir.
Okay, okay.
What about you asking? In the
Hello.
sir,
Yeah, yeah.
are you hear my voice,
Mm-hmm.
sir?
Yes, yes, I can hear you. What about others? Subha and 4 others are there.
Sir, myself Pavitra.
Mm-hmm.
Actually, I'm from engineering college professor, sir, assistant
Okay, okay,
professor.
okay, okay. Okay, so all sorts of people are there. Okay. So, what do you guys feel? I mean, the courses or the questions are going beyond a bit difficult, or is it okay? So, please tell me, because otherwise I will continue to do in whatever I think, but it will not help you guys, or it may help, but it may be difficult or not relevant for that course itself. Is it helping in solving assignments, or let's say a bit beyond the assignment also?
This type of explanation, okay, sir. No problem, sir.
Okay, okay.
Helping for assignment and otherwise other extra.
So today I learned that this is a UG level course. I was thinking that this is a PG level course, but anyway. Okay, let's end then. Thank you for joining, and again, please be interact. I mean, interact with us so that it helps us. And if you're solving the problem or you're able to solve the problem, we'll get to know. Otherwise, it's anyway online, so we can't face each other. It's very difficult to get the feel what you guys are doing, or the level of this tutorial session and the course overall. Okay, so thank you for joining. I'm ending the meeting.
Thank you, sir.
Thank you.